Hello everyone. I welcome you all to the next topic in computer networks, UGC NET syllabus. And the next topic is noiseless channels and noisy channels. So you may ask me, what is a noiseless channel, right? So when you transmit any data over a channel and when there are no losses in data or when there is no error in the data that you are passing it, and there are no distortion or attenuation in the signal, such a channel is called as a noiseless channels. And you can ask me, what is a noisy channel? So noisy channels are the channels when you pass your data or signal through those channels, the data get lost or the data may end up in error and the signal may be lost or the signal may get distorted or it may get attenuated. So such channels are called as a noisy channels. So when you want to go deeply or when you want to learn deeply about the noisy channels, there are basically four kinds of noises that the data may experience. So the first type is thermal noise. So thermal noise is due to the thermal agitation of electrons present in the signals, and it is also called as a white noise. And you may expect problems like compute the thermal noise with a bandwidth 1 hertz in any device or conductor. So here the bandwidth is constant, which means the bandwidth is always always the bandwidth is 1 hertz. So at that time, you can use the formula N naught, which is the thermal noise is equal to K into T watts per hertz. K into T watts per hertz. So where K is the Boltzmann constant and its value is 1.38 into 10 power minus 23 joules per Kelvin. See here, you can find it here. This is the Boltzmann constant, and you can substitute this constant in the place of K. And what is this T? T is the temperature in kelvins. T is the temperature in kelvins, and it is given in the problem. See, you can work out this problem. They have given T is equal to 17 degrees centigrade or 290 Kelvin. They have given in terms of Kelvin as well as in centigrade. And we are going to compute the thermal noise for this given temperature. And in place of K, I'm substituting this Boltzmann constant, which is 1.38 into 10 power minus 23. And since the Boltzmann constant is in joules per Kelvin, I'm substituting this 290 Kelvin temperature value here. And when I multiply these two things, I'm getting the value 4 into 10 power minus 21 watts per hertz. Okay, so this is the way we compute our thermal noise. And here I'm going to convert this 4 into 10 power minus 21 watts per hertz into decibel watts per hertz. So into this decibel watts per hertz. So this is how it is computed. The thermal noise is computed and for the bandwidth of 1 hertz. So when you have other bandwidths, you have to substitute the bandwidth value also. So at that time, you can compute the thermal noise as N is equal to K into T into bandwidth. Okay. So if you want to express this K, T and T in decibel watts, if they ask you to express this in decibel watts, so decibel watts, see here, the answer is expressed in decibel watts. At that time, you have to take the log value and then multiply the value by 10. Okay, so 10 log K plus 10 log T plus 10 log B. This is the formula for computing the thermal noise in terms of decibel watts. So they have given the sum here 294 Kelvin, only the temperature they have given. And here they have given the specific bandwidth 10 megahertz. So now they are asking to compute the thermal noise at the receiver's output. So I'm substituting this formula. So in place of K, I'm substituting the Boltzmann constant. And in place of T, I'm substituting 294 Kelvin. And in place of B, bandwidth, they have given megahertz. So 10 power 7. So we are substituting it and finding the log value and multiplying by 10. We are getting this decibel watts. So this is how the thermal noise is computed. And the next type of noise is an intermodulation noise. So which is when you have two signals at two different frequencies, when they are transmitted together, they may collide and they form a new frequency level. so in which the signals may get distorted, that you may experience some interferences. So that is called as the intermodulation noise. Okay. Next is a crosstalk, which is experienced like anyone talking in between when the signal is transmitting. So you may hear some other conversation other than yours. That is called as a crosstalk. And what is called as an impulse noise, when you experience sharp noises or spikes of noises in between your transmission, that is called as an impulse noise. So these are the four categories of noises: thermal noise or white noise, intermodulation noise, crosstalk noise, and impulse noise. These are the kinds of noises you can experience in the noisy channels. So this is what the main thing about the noisy channel. And you have to know how to compute the bandwidth for this noisy channels and noiseless channels. So for that, we have Nyquist limit and Shannon's limit. How to compute or how to work on the problems on Nyquist limit and Shannon's limit, we will follow up in the next video. Thank you all for watching. Thank you. Have a nice day.